We're going to start this video by talking about Gaston Geometry. Now, in Chapter 3, we used the relationships between amounts in moles and masses of reactants and products to solve stoichiometry problems. In the same manner, we're going to use it in this chapter. The only difference is that we're going to use the relationships between moles and volume instead of moles and grams. Here I'm showing you figure 5.13, which shows you the pathway for Gaston Geometry. You start out with grams or volume, and you can convert that to moles of reactant, then go to moles of the product, of course through mole to mole ratio, and then use the amount, convert that to the amount in grams or volume. Let's try to do a problem. It says calculate the volume of O2 in liters required for the complete combustion of 7.64 liters of acetylene, which is C2H2, measured at the same temperature and pressure. Here we're relating volume and number of moles. So right there and then you should know that you're dealing with Avogadro's law. But regardless, we start out with the main equation. It's PV equals nRT. And we know that they're talking about volume and moles. So we isolate V1 and N1 on one side. So it'd be V1 divided by N1 is equal to V2 divided by N2. And they tell you that temperature and pressure are constant, and of course R is constant. So all you have to do now is isolate V1 because they want to calculate the volume of O2. So V1 would equal V2 times N1 divided by N2. So all you would have to do is figure out the moles for both of the compounds. And you have that because you have the balanced equation right there. So V2, which is of course is the volume of the second component, would be 7.64 of acetylene. What would be N1? N1 is O2, and that, looking at the balanced equation, is 5 moles. You have 5 moles of O2 in this reaction. And then that divided by the moles of the second component. The second component is, of course, acetylene. And you look at the balanced equation, and it's 2. So all you would do is take 7.64 times 5 divided by 2. And that ends up being 19.1 liters. Remember that you could do this because Avogadro's law states that two different gases that have the same volume will have the same number of moles. So that's why you can make this relationship. Let's try another one. The problem says the equation for the metabolic breakdown of glucose, C6H12O6, is the same as the equation for the combustion of glucose in air. And then they give you the chemical reaction. It's 1 mole of glucose plus 6 moles of oxygen gas yields 6 moles of carbon dioxide gas plus 6 moles of water. The actual question is, calculate the volume of carbon dioxide produced at 37 degrees Celsius and 1 atm when 5.6 grams of glucose is used up in the reaction. We eventually are going to have to set up the same equation we just did, but before we do that, we have to figure out what the volume is because they don't tell you that in this problem. So they give you all the information for glucose, and we would have to then use that and put that into the final equation. So what I mean is, of course, we start out with the main equation of chapter 5, PV equals nRT. I solve for volume 1, which I'm going to designate, the first volume is going to be the glucose, okay? So I'm going to isolate volume, and then I have the moles of glucose, RT over pressure of glucose. To find the moles of glucose, I don't have that, but they do give me the amount in grams of glucose. So all I do is convert that to moles of glucose through the molar mass. I end up having 0.0311. I multiply that times the gas constant. I multiply that times the temperature in kelvins, which is 310.15, and I divide all that into 1 atm. That gives me a volume of 0.79177. The original question asked calculate the volume of CO2, so that would be my V2. My V2 is going to equal to V1, which we just found out, times N2 divided by N1. For those moles, all I got to do is now look at the balanced equation. N2, which is carbon dioxide, there's 6 moles, so I put 0.79177 times 6 divided by the moles of N1, which is the moles of glucose in the balanced equation. So it's basically 0.79177 times 6 divided by 1. It ends up being 4.75 liters of carbon dioxide. This is basically what gas stoichiometry is. All you need to do is practice them. Practice these problems a lot because they're exactly the same as the ones we've been doing before. The only thing that's different is now we're dealing with gases. You can tell that there's not much to it because the section, which is 5.5 of your book, is really tiny. Alright, now let's talk about Dalton's Law of partial pressures. So far, we've only concentrated on the behavior of pure gases, but very often we actually experience problems where a mixture of gases are involved. So to do that, we need to take into account their partial pressures. So partial pressures is the pressure of an individual gas inside a mixture. In 1801, Dalton stated his law of partial pressures, which basically states that the total pressure of a mixture of gases is just the sum of the pressures that each gas would exert if it were present alone. So all it is if you have a mixture of gases, you take the pressures of each individual gas and you add them up. That's it. Let's consider a case in which we have two gases, A and B, and they're in a container of volume V. If I wanted to find the pressure of gas A, all I would do is solve for pressure. So PA is equal to NA RT over V. All we're doing is using the PV equals nRT equation and solving for pressure. Okay, so now I want to do the same thing for gas B. Let's solve for the pressure of gas B. So PB is equal to NB RT over V. Okay, we just learned that if I wanted to find the total pressure of a mixture of gases, all I have to do is sum up the two different pressures for the two different gases. So we just defined what PA and PB was, so let's go ahead and plug that into this new equation. So PT, total pressure, is equal to PA, which we just defined, is NA RT over V, plus NB RT over V. If you notice, we have RT over V, which is the same in both fractions, so we can collect like terms and leave inside the parentheses what's not the same, which is NA plus NB. So you end up with an equation that says PT is equal to RT over V times parentheses NA plus NB close parentheses. Okay, awesome. So now, what if I asked you, how does the pressure of gas A, relate to the total pressure of the system? So basically, I want to know, how does the pressure of one gas relate to the total pressure of everybody in that mixture? So I would take its PA divided by PT. Okay, so this is basically part over whole. So I would take PA, which I've already defined, is NART over V divided by the total pressure, which we also just defined. It's RT over V times parentheses NA plus NB close parentheses. If you notice, RT and V can cancel out. So all you're left with is the moles of A divided by the sum of A and B. This is what we call mole fraction. That's the X. Okay, that's the symbol that we have for it. Basically, it's part over whole. That's all it is. Mole fraction it's a dimensionless quantity that expresses the ratio of the number of moles of one component to the number of moles of all components that are present in the mixture. And it is a dimensionless quantity because it's moles over moles, basically. And if you have that, you're going to cancel all the units out, and all you have is just the number. That's basically it. So if I asked you, what is the partial pressure of whatever, you would use this equation down here. Partial pressure of whatever is equal to the mole fraction of whatever. And remember that mole fraction is part over whole of everybody times the total pressure of the entire system. This looks a little bit complicated, but I promise you this is the easiest type of problem we have all semester. All right, let's practice some problems. This is practice exercise on page 198 of your book. It reads, a sample of natural gas contains 8.24 moles of methane, CH4, 0.421 moles of ethane, C2H6, and 0.116 moles of propane, C3H8. If the total pressure of the gases is 1.37 atm, what are the partial pressures of each gas? When I do these problems, I write everything down. So I'm going to write that there's 8.24 moles of CH4, 0.421 moles of C2H6, 0.116 moles of C3H8, and I have a total pressure of 1.37, excuse me. They want to know the partial pressure, so I know that I have to use the equation that we just learned. Partial pressure is equal to mole fraction times total pressure. All right, so for the mole fraction, I'm going to have to take the moles of everybody, because remember, it's part over whole, but I need to figure out what the whole is. So they give me the moles of everybody, so all I do is add everybody up. So if I add 8.24, 0.421, and 0.116, I end up with 8.777. I'm going to use that when I find the partial pressures of each of these gases. All right, so now I'm ready to use the partial pressure equation. To find the partial pressure of methane, I write P sub CH4 is equal to X sub CH4 times the total pressure. X would be the part of methane over the whole system. The part of methane is 8.24 moles. So I would say 8.24 divided by 8.777, that's what we calculated as the whole mole for the entire system, times the total pressure, which they gave us, 1.37. So 8.24 divided by 8.777 times 1.37 is equal to a partial pressure for methane of 1.28 atm. I'm done with methane. Now all I got to do is do the same thing for ethane and propane. So I write partial pressure of ethane is equal to the mole fraction of ethane. Okay, so mole fraction for ethane is the part, right? That's the top part, is 0.421 divided by the whole, which is 8.777, times the total pressure of the system, which is 1.37. I get a partial pressure of ethane of 0.0657. I do the exact same thing for propane, and I end up having a partial pressure of propane of 0.018106. I'm basically done. That's the entire problem. A good way to check if your answer is correct is to add up all of the partial pressures. They should all add up to the total pressure that they gave you. So basically, if you add the 1.28, the partial pressure of ethane and propane together, it should add up to 1.37 atm, which it does. All right, so that's all I want to cover in this video. You are going to be responsible for using partial pressures when calculating volumes of gases collected over water. That's the last section in Chapter 5 that you're going to be responsible for. We're going to do all of these problems on Wednesday in class.